Thank you very much, Daniele, and thank you all for being here. I would like to thank also Patrick and Barbara for organizing this nice workshop, and also Barbara more generally for organizing all this series of workshops. I enjoyed attending most of them, and I'm of course very happy to contribute to this one with this presentation. So like all the presentations that we've heard so far, I will talk about flow in the deep earth, but maybe the specificity of my presentation is that I will focus on a very short period of the Earth's history, which is something like the 100 million years. It's very short compared to the age of the Earth, but it's a very important period that we need to constrain as best as we can, because it sort of sets up the initial condition from which the Earth has evolved until present. And during this short period of time, I will focus on a particular event, which is core formation, basically the separation of iron and silicate to form an iron surrounded by a silicate mantle, as we have for the Earth, but also other terrestrial bodies. This is clearly the most important and the first differentiation event that the Earth has experienced. And even if it was, happened a long time ago, there are some important constraints that we can use to better understand what happened. So I'm going to review them very briefly. I put 3 of them. One is the timing constraint that comes from cosmochemistry. We know that core formation is a relatively fast process that has been achieved within a few tens of million years for planets of the size of the Earth. And another constraint comes from the so-called overabundance of siderophile element in the Earth's mantle, which suggests that core formation is also a high temperature but a high pressure process. The other thing that this constraint tells us is that this overabundance also suggests that there's, even though core formation is a fast process, it's at least slow enough to allow some chemical equilibration between the metal and the silicate, which occurs through diffusion. And finally, the last constraint is a constraint that concerns the mechanism of separation of the metal and the silicate. We have 2 very different elements with 2 very different densities, and of course, gravitational segregation is an efficient way of separating those elements. But for this, you need to have a high temperature in order to have low viscosities, so that this mechanism can be efficient enough. So despite those constraints, there are several possible scenarios that can be considered for core formation, and most of them are summarized in this cartoon. We can think about the percolation of iron to a silicate matrix, or the propagation of iron cracks in a solid Proto-Mantle, or also what people call sometimes the scenario of negative diapirism, in which you have large blobs of metal that are sinking through a silicate, which is magma ocean, which is molten or partially molten. And this is the scenario I will focus for the rest of my presentation. And I will try to address at least partially a few important questions regarding this scenario. The most important question I want to address is whether those diapir break up or not. And then what are the consequences on the metal-silicate chemical exchanges and also heat partitioning at the end of my talk. So this is basically the outline of my presentation. This is a very basic fluid dynamic problem, and it can be described by fluid dynamics governing equations. There are 3 here. The first one is the conservation of momentum. It's basically Newton's law that is generalized for a fluid. We have mass conservation and conservation of composition. We deal with 2 different compositions, one for the silicate here and the metal here. And they are non-dimensionalized, so you see in red all the governing dimensionless parameters that we like to work with in fluid dynamics. They all express the importance of a physical process with respect to inertia here. The Reynolds number expresses the relative importance of viscous effect. The Froude number expresses the importance of buoyancy, and the Weber number expresses the importance of surface tension. And in addition to those parameters, we also need to care very much about the rheology, the rheological parameter in particular of the silicate magma ocean, and I will talk about this as well. So there are 2 ways to model this scenario. One is by doing numerical experiments, by solving numerically the equation that I just showed. This is what I do along with other people, and you can also do the same type of experiment in a tank, similar to what Andabai has shown, also Cinzia in her talk yesterday. And I'm not certainly going to say that one is better than the other. They all have their own advantage and inconvenience. But for a numerical experiment, one inconvenience is, is a frequent belief that perhaps is best summarized by this quote from Albert Einstein. A theory is something that nobody believes except the person who made it, and an experiment is something everybody believes except the person who made it. And so I see some people smiling, so you must know what I'm talking about, and it applies well to a laboratory experiment and a numerical experiment, and I borrowed this analogy from a talk I heard years ago by Georges Bergantz, and even though it's a little bit caricatural, there's a little bit of truth behind it. And this is the reason why I always try to convince other people than just myself that the numerical experiments I'm performing are reliable and can be trusted. And for that, I will try to do it with only one slide. And for that, for those experiments, I'm using a 3D finite volume code that I entirely developed myself. So it's a bit time-consuming, but it has the advantage of knowing what I put in. Put in exactly, and I put in a high order and accurate scheme and also robust scheme to solve for the Navier-Stokes equation that can be used for both small and low values of the Reynolds number. And I want to spend just a few more seconds on the conservation of composition, because this is one of the main difficulties of this type of modeling. Because we are dealing with a sharply varying field, and instead of modeling this sharply varying field, I use a level set method. This is basically, I replace this field by a smoothly varying field, and the value of this field equal to 0 represents the location of the interface. The great advantage in doing so, again on a refined grid here, is that you can calculate very accurately spatial derivative across the interface, which are required to estimate and to impose the surface tension force that apply exactly at the interface between the metal and the silicate. And in addition to that, I also use Lagrangian particle to correct for any possible inaccuracies when advecting this smooth varying field. This allows to have a very good mass preservation at all time with less than 1% error. Last but not least, the code has been benchmarked against many analytical and numerical solutions, and also compared with success to analog experiments. So we want to know what is the parameter space. I mentioned earlier that there were 3 governing parameters. Instead, here I'm only considering 2, because the full number is not independent of the Reynolds number, so I won't be talking about it. And we want to know what is the plausible range of this Reynolds and Weber number, which actually can be quite large, because the parameter that enters into those numbers can vary by several orders of magnitude. For instance, the dipole radius can be as small as a few millimeters to as large as a few hundreds of kilometers. And the silicate viscosity, which is by far the greatest unknown in this problem, can vary easily by 20 orders of magnitude. So as a consequence, if you plot those, the value of those numbers as a function of those 2 parameters, you can get a plausible range of variation by 20 orders of magnitude for both of those parameters, which is not negligible. And things get even worse if you now consider a partially molten magma ocean. Here the color scale is completely saturated, but you can, I can tell you that this stretches out the range of plausible variation by over 100 of orders of magnitude, and that's a lot. So the other point I want to make here is that not only high values of the Weber and the Reynolds number need to be considered. Sometimes people argue that they are more realistic for a magma ocean stage, but clearly if you look at those values, not only large but small and intermediate values of these numbers must be also explored. So we cannot explore this full range of parameters, but what we can do instead is to consider this green area here, which corresponds to values of those Weber and Reynolds number, lower or greater than 1 plus or minus 3 orders of magnitude. This allows to understand the dynamics for all those different regimes, and that's what I'm going to show you in the next slides. This represents something like 200 experiments, and some other are still ongoing as I speak. So I will directly jump into the effect of the governing parameter on the dynamics here. Keep in mind that what I'm really interested in, first of all, is to determine whether or not the diapir will break up as they sink towards the bottom of the magma ocean. And I will start by looking at the influence of the Reynolds number without any surface tension effect. What you will see in these movies is the surface of the interface between the metal and the silicate. And we are looking in this is a moving frame of reference, or we are following the diapir as they sink. So I start with the first case of a Reynolds number of 1. That means inertia and viscous effect are more or less equally important. And what you see is that the shape of the diapir changes a little bit, but there's no breakup that can be observed here. Now, if we increase the Reynolds number by an order of magnitude, you can see that the deformation is more important. It leads to a breakup event. And finally, the resulting size of this breakup event will be and are now 4 diapirs of almost identical size, which remain stable. Now, if we do the same experiments with a further increase by an order of magnitude, we see not just one, but several successive breakup events that lead to the formation, with turbulent motion that you can guess, the formation of iron droplets. So to sum up, large values of the Reynolds number leads to a breakup, and the post-breakup diapir size will decrease with increasing the value of the Reynolds number. Now, if we continue on that, but add just a little bit of surface tension. Surface tension, I'm sure you are all familiar with. This is the reason why water droplet on the table has this oval shape, and it also acts the same way in a magma ocean. And here I started with the same case I showed earlier with the Reynolds number of 100, but I add a little bit of surface tension with a Weber number of 1,000. That's not much of a surface tension, but you will see that already there are differences. So there are still several episodes of breakup, but the resulting size of the diapir is much larger than the droplets that we've seen in a previous movie, and this is due to the action of surface tension. Now, if we increase the importance of surface tension, that means decreasing the value of the Weber number, you see that you have again a breakup occurring, but the resulting size of this after breakup is just 4 diapir of almost identical size, like we've seen in the previous slide, actually. And finally, for an even stronger case with stronger surface tension, no breakup is happening. The shape of the diapir changes from spherical to hemispherical, but there's no breakup. So surface tension, if it's strong enough, can efficiently reduce and even prevent breakup. So we can summarize that in a Weber and a Reynolds space and map out the regions where the diapir are stable or unstable, and the boundary between these two regions can be determined actually using a simple theoretical breakup criterion, which is based on Newton's law, basically looking at the imbalance between the forces that are acting against breakup, which is surface tension and the viscous resistance to deformation, and the force that is acting for breakup, which is the drag force. So that's how it works with the effect of the Reynolds and the Weber number. Now I want to focus on the effect of rheology. Again, this is the key here. And this is the same plot that I've showed earlier. This corresponds to a case where the diapir and the silicate magma ocean have the same viscosity. This is given by this parameter here, lambda. Yesterday, Cinzia used a different Greek letter. She called it lambda, but that's the same meaning exactly. And if you do now the same type of diagram, but for a case where the viscosity inside the diapir is 1,000 times less viscous, then you clearly see that the stable and unstable area are not the same. And at high values of the Reynolds number, this has also been found by recent analog experiments. The internal circulation, which is favored by low viscosity, helps to maintain the diapir shape without breaking up. But we have exactly the opposite effect at low or intermediate values of the Reynolds number, because the viscous resistance to deformation, which is enhanced by increasing the viscosity of the diapir, tends also to prevent breakup. So we have this sort of opposite effect of this viscosity contrast depending on the value of the Reynolds number. Now I want to talk about the effect of non-Newtonian viscosity because if we now consider a magma ocean that is not completely molten, which is partially molten, experiments have shown that the crystallization leads to a change in the rheological behavior from Newtonian viscosity to non-Newtonian case, where you have a stress dependence of the viscosity with a power law index that, as we've seen yesterday, for instance, in some presentation. You have here this guy, which is a transition stress, above which the viscosity is mainly non-Newtonian, and below which the viscosity is mainly Newtonian. So this is what I've considered for the case that I will show you in the next slide. This is for a Newtonian case. For those two experiments here, this is non-Newtonian. I keep the same value of the Reynolds and the Weber number, and you will see that the shape of the diapir changes a little bit. It flattens, a small amplitude oscillation, but it doesn't break up. If we do now the same experiment for the non-Newtonian case, you see that you have much larger amplitude variation of this diapir shape. We are really at the boundary to break up. And this also can be seen by looking at the diapir sinking velocity. You see those large amplitude oscillation corresponding to this case. And this difference is due to the fact that in the Newtonian case, again, the viscosity is constant in either the silicate or the metal, while in the non-Newtonian case, there is a strong dependence with the stress, and so there's this feedback mechanism that changes constantly the viscosity in the silicate magma ocean, and this tends to favor breakup. And the breakup, this effect of non-Newtonian rheology can best be seen by comparing those stability diagrams. This is for the Newtonian case, the same diagram that I showed earlier. This is for the non-Newtonian case, and clearly at low values of the Reynolds number, the red area is larger here than here, again, meaning that the non-Newtonian rheology favors breakup. So we can use we can constrain this different stability as a function. I mean, using the criteria that I mentioned earlier, and we can map as a function of the size of those diapir and the viscosity of the magma ocean, the region where the diapir would break up in blue, in gray, and the region where the diapir won't break up in blue. So if you consider a diapir laying somewhere in this blue area, nothing is going to happen to it. It will sink towards the bottom of the magma ocean without breaking up. But if you now consider a diapir somewhere in this unstable area, it cannot stay there, so it has to move towards this stable area, and it will do this horizontally by successive breakup events. And those successive breakup events, I should mention, occur on a very short distances. This is something that I've seen in several, axisymmetric geometry, also with those 3D, without the experiment that I've showed, without imposing any symmetry. The breakup stage it's always a two-stage breakup. You first stretch horizontally the diapir because the drag force impose a stagnation point just in front of the diapir, which stretches this diapir horizontally until it breaks up. And again, the breakup sequence takes less than a sinking distance less than or comparable to the size of the diapir, and this also is consistent with analog experiments. And now if we want to look at the implication on the metal silicate chemical exchanges, we can do that by simply looking for solution of fixed law. This is basically a diffusion equation, and in the simplest case we can find an analytical solution in which appears here this Peclet number. This is a number that measures the importance of advection over diffusion velocities, and we want to know how much of a sinking diapir can equilibrate chemically with the surrounding silicate magma ocean. And we can use this equation to infer the equilibration distance, which is necessary for that, as a function of the magma ocean viscosity. And you can see that for most values of the magma ocean viscosity, which are quite low, the equilibration distance is usually less than a few kilometers, which is much less than what you would think for plausible value of the thickness of a magma ocean. So equilibration, total equilibration is very likely. But if you now go to higher values that could correspond to partially molten but still Newtonian magma ocean, then the equilibration distance is comparable to, can be comparable, even larger than the thickness of a magma ocean. So in that case, it's not clear whether complete equilibration can occur. If you now do the same exercise with a partially molten non-Newtonian magma ocean, that is for basically higher also values of the silicate magma ocean viscosity, then you get values that are much larger than the thickness of the magma ocean, even larger than the Earth itself. So clearly, its complete equilibration is very unlikely in this case. And finally, this is the last thing I want to talk about. I want to talk about viscous heating and heat partitioning during core formation. It shows this artist's view of a spaceship coming back into the Earth's atmosphere, which has really nothing to do with core formation. But the thing that I want to draw your attention on is this increase in temperature in the vicinity of this spaceship, which occurs through the conversion of gravitational potential energy into kinetic energy and eventually into heat. And this is exactly the same mechanism that occurs during the sinking of those iron diapirs in the silicate magma ocean. So it's not so hard to estimate the gravitational potential energy that is available, but what is much more difficult to guess is how this energy and this heat is going to partition between the metal and the silicate. So we can do that. You can study that by supplementing the three governing equations by a fourth equation, to conservation equation for the conservation of energy, internal energy. We have here on the right-hand side diffusion, and this represents viscous heating. And I'm going to show you how viscous dissipation takes place in the vicinity of the diapir, which is shown here. The interface is shown here in white, and you can see that very quickly that the dissipation is maximum at the boundary between the diapir and the silicate magma ocean, but it's located mostly outside of the diapir, and that's very important because it means that the increase of in temperature will, due to viscous heating, is mostly going to be outside of the diapir, and part of this heat is going to be transferred from the silicate to the diapir via diffusion. And this is why the diapir temperature keeps on increasing towards an asymptotic value if you let it go for long enough. And this is, this could represent in terms of dimensional units something like a few hundreds to a few thousands of Kelvin, so that's not negligible. Now, let's do the same exercise for a non-Newtonian silicate magma ocean, but keeping the rest, the other parameters the same. And clearly, there's a big difference here because the rheology leads to a very different dissipation, which I don't show here, but anyway, it leads to a very different heat partitioning between the metal and the silicate, even though the available potential energy is the same for both cases. And things are even more interesting if you consider a case where you have breakup and case where you don't have breakup. In blue, that's a case where you have strong surface tension, so there's no breakup, but in red, you have no surface tension, and the diapir will break up about here. And you can see that the dynamic history leads to a very different heat partitioning between the metal and the silicate. 1 minute, okay, no problem. So, yes, so this has an important implication for the early Earth's thermal state, because if you consider not just one, but thousands of those diapirs sinking towards the center of a planet, they will tend to leave a thermal profile that looks like this, a hotter lowermost mantle, a relatively hot core. It can be even hotter than the mantle. It depends on the size of the diapir. And it can explain things like, for instance, the basal magma ocean, as it has been proposed a few years ago. The last figure that I want to show here is this one. This is the fraction of viscous heating of heat produced by viscous heating that is remains in the silicate part as a function of the size of the diapir. And the larger the diapir, the more important is this fraction. That means that the larger the diapir, the colder will be the core resulting from a core formation. So this can be also used, or this can have an implication to explain the presence or the absence and the sustainability of a geodynamo on planets like the Earth or Mars. So these are my conclusions. I'm running out of time, so I'm going to skip them very quickly. The main message here is that core formation has a huge influence on the Earth's evolution. One of the key aspects here is the rheology, and it has a strong influence on the dynamics, on the thermal, on the heat partitioning, and on the chemical exchanges. And this is the reason why we really need better constraints on the rheology of the silicate. For the partially molten case and for the fully molten case, we need better constraint on this transition stress I mentioned as a function of melt fraction, pressure, composition, and the same for the viscosity, because of course we can always derive scaling laws, but at some point we need to feed them with some numbers, so this would really help to say something useful about the Earth. So yes, I won't talk about it because I didn't have time. But I would like to thank my sponsors that enabled me to do this work in a rather good condition. I would like to thank you for your attention.